So in this video, we're going to talk about a very common laboratory technique. It's usually referred to as collecting a gas over water. So, thinking about it, in a chemical reaction, you make some type of gas. It's usually hard to trap that gas in some type of container. If you think about, we've done a lab before where we had a bottle where we mixed baking soda plus vinegar. And we were trying to prove the conservation of mass. So water, the gas was being made, so most groups put a balloon over the top. That's one way to measure and trap the gas. But the problem is that doesn't allow us to accurately measure the volume of the gas because the volume of the balloon can change, it can stretch. So there's a simple lab technique called collecting gas over water that will allow you to determine the exact volume of a gas created in a lab. And we're going to do this when we do the molar mass of butane lab. So here's a simple diagram, not showing the real equipment, but showing pictures of what the equipment looks like for an example. So let's say here in a beaker, we have some chemical reaction. Let's say it's the same reaction that we've seen before where we take baking soda plus vinegar. We know one of the products of that is carbon dioxide gas. What we can do is if we seal this flask, except for one straw, or one test tube here, the gas that's produced only has one place to go, up and through the straw. And then we can curve that straw or curve that into any particular place. So we can direct that gas to wherever we want it to go. In this case, we're going to direct it over into a trough or just some bucket with water in it. And in that bucket, we have a test tube that was upside down. But before we put that test tube upside down, we had the test tube right side up, and we filled it with water up to the very top. Then we flip it upside down, and we hold something underneath so it stays filled with water. Then we put it into our bucket. And because of air pressure pushing down here, that keeps the water inside the test tube. Now, that gas, though, that's traveling through this tube eventually gets into the water, and it gets released right underneath the test tube, and it rises up. Well, once that air is coming into the test tube, it has to take up some space. It has some volume. What it does is when the air goes inside, that is actually pushing out some of the water that was in the test tube. So therefore, two things are going to happen. A, the height of this water is going to go up, because water is coming out of the test tube and into the bucket. And B, we're going to make a little pocket here of gas. And if we have a test tube with markings on it, we can then figure out the exact volume of gas that's being created. And then we can apply all the gas laws that we know, PV equals nRT, any pressure, temperature, volume relationship, in order to do calculations. Now there's one small wrinkle associated with this. Because when you are creating this gas, this space right here doesn't just have CO2 gas in it, the gas that we're making from the reaction. It also has some water vapor in it, because there's water on the inside of that beaker, on the walls. Some of that water, H2O liquid, is going to naturally turn into a gas. So we really have a mixture. We have two gases, the gas that we're trying to collect and some water vapor. So therefore, we have to correct for the fact that there's some water vapor present. We have to use the concept of partial pressures. So the total pressure inside this region here would be the pressure of the CO2 or whatever gas you're collecting, plus the pressure of H2O. Well, how do you figure out the pressure of the H2O? It depends on the temperature of the water. So here's a table that tells us the exact vapor pressure of water depending on the temperature. So we can see when the temperature is 16 degrees Celsius, that water in the bucket's 16 degrees Celsius, the partial pressure of H2O is equal to 13.6 millimeters of mercury, which is the same thing as torr. As we can tell, the pressure changes with temperature. In general, as the temperature increases, the pressure is increasing. And the logic for that is pretty simple. If you have a sealed container with water in it at, let's say, 16 degrees Celsius, and over here we have a sealed container with water in it at, let's say, 25 degrees Celsius, the water molecules here have more kinetic energy. They're moving faster. So some of them have enough energy actually to move from the liquid into the gaseous phase. Same thing happening over here, but since this is at a lower temperature, these molecules have less kinetic energy. So fewer of them are going to turn into a gas. So if over here we have more gas molecules, that means we have more collisions, which means we have a greater pressure. So that doesn't actually matter conceptually when we're doing this lab, but it's just an interesting to make a note of. We can explain these trends very simply. But how do we apply them to a problem? This will be like similar to what we're doing in the lab. A sample of hydrogen gas is collected over water at 22 degrees Celsius. The total pressure of the gas is 0.989 atmospheres. What is the pressure of the gas sample? Well, it's collected over water. So that means we have some reaction where gas is being made, going into some trough. Boom, it's filled with water. And there's a test tube above it right here that was filled with water. And this gas is going inside and taking up some of this space. So we know the total pressure is equal to the pressure of the hydrogen gas and the pressure of the water. So 0.989 is equal to the pressure of the hydrogen gas plus the pressure of the water. Well, how do we figure it out? It's not given. Oh, well, I know the water is at 22 degrees Celsius. So if I look back at this table, I see that the pressure of water at 22 degrees Celsius is 19.8 millimeters of mercury. So since we're dealing in ATM though, I got to convert 19.8 mmHg divided by 760 in 1 atmosphere. If you go ahead and do the math for that, 19.8 divided by 760, we get 0.02605, 0.02605. Subtract from that on both sides. And what we would get for a final answer for the pressure of the hydrogen gas would be 0.96 with sig figs 3 ATM. So as you can see, this is pretty dang close to the total pressure, but it's slightly lower, and that's because there is some other pressure caused by the water vapor present. So in the lab, we will be collecting a gas, butane, over water, and we'll have to make this correction. Our setup will be similar to this, but slightly different, but the concept will still be the same.